Another example we're going to look at here is 4C8. So in this example, we have an arm with a length L. One end of the arm is fixed at point O, and on the other end of the arm, there's a box A attached to the arm. And at the initial position, A is at a rest position, and at that moment there's a bullet with a speed VB1, and after impact from the bullet, both A and bullet B will stick together. So this mass A and B will swing the bar, the M, to a certain angle. Let's call it theta. And in this case, in this example, we need to find what is the angle theta, and also what is the energy loss from this system after impact. Okay, so by looking at the given condition of this problem, it tells us both A and B stick together after impact. That tells us a very important information, which is E equals to 0. And that's perfectly inelastic impact. And that's also tell us after impact, both A and B will be moving at the same speed. That's called VAB2. Okay, then first look at A and B. During the impact, we can set up our T and N coordinate system as N as the line of impact, T as the plane of contact. Then we can apply a linear impulse momentum equation on N direction, which is the horizontal direction. And on horizontal direction, we don't have any forces, right? All the forces will be pointing either its tension force or gravitational force on T direction. We don't have any forces on N direction. Therefore, the sum of forces equals 0. That implies the conservation of momentum on N direction. And then sum of forces equal to 0, so the left hand of equation equals to 0. And on the right hand of equation, we can have the masses of A and B times VAB2, that's the speed they're moving after impact, minus MB times VB1. Then if you look at this, let's call this equation 1. The only unknown here is VAB2. And we know VB1, we know MA and MB, and we can solve what is VAB2. But this is not what this problem is asking for. We need to find what is the theta this arm will swing after the impact. So we will need to use work energy equation. Only apply this work energy equation after impact. And from work energy equation, we know T2 plus TV2 equals T1 plus B1 plus U, which is the work done by the non-conservative forces from position 1 to 2. And T2, it's a kinetic energy at position 1. That's position 1 adds the position right after impact. Keep that in mind. So T1 equals 1 over 2 times MA plus MB times VAB2 squared. Right, that's both bullet and the block A moving together with the velocity VAB2, and we just find that speed right there. And the kinetic energy at position 2, that is the kinetic energy when the bars swing to the angle theta. We know that's a maximum height it can go, so there's no kinetic energy at position 2. And therefore position 2 equals 0. And V1, it's a potential energy at position 1. We can set a reference point zero reference uh, zero potential energy reference point at the initial position, and then that will give us V1 equal to 0, and the potential energy at V2 gonna be ma plus mb times g times the height, right, times h. But this gonna depends on how how far both b and a moves. So that's a distance h there, and h can be solved by you look at this triangle, and we know L, which is the length of the arm, we know theta, and so H equals to L minus this length B from O to that point, and it equals L times cosine theta. So H equals L minus L cosine theta, and that will give us the potential energy at position 2. The work done from the non-conservative force will be 0 because we don't have any friction here. And now you can plug all the components into the work energy equation, and you will realize that this cosine theta is the only unknown and can be written as cosine theta equals GL minus 1 over 2 VAB2 square, and you can find out what is theta. And in terms of energy loss, you can calculate what is the kinetic energy right before impact. That's only the bullet B carries all the kinetic energy, which is 1 over 2 mb times VB1 square. And that energy minus what's the energy left in the system right after impact, that would be the sum of the mass from A and B times the speed they're traveling, which is VAB2 square. And you'll realize the energy loss, the difference between these two, is not equal to 0, and that means we do have energy loss during the impact. And that tells you a very important conclusion: the conservation of momentum does not mean the conservation of energy. And the special case is only if your E equals to 1, that implies no energy loss during impact. Alright, this is